Welcome to General Chemistry Mini Lecture Series, Lecture 56, Kinetic Molecular Theory. Lecture 56 now. Kinetic Molecular Theory. First, let's take a look at gas particle volume. So this means the volume of individual gas particles. The gas particles do have mass, but we consider them have no volume. Second, let's take a look at the motion of those gas particles. The movement of gas particles is always a straight line, except when they collide with each other or with the container walls. When the moving particle hit another particle or the container, they don't stick in there, but they bounce off. So you see here, bounce off and continue moving in another direction, but still in a straight line motion. So the average distance between collisions is the mean free path between collision, like here. That's the distance here. And now when the collision just happened, of course, then that distance is very small. Speaking of gas particle collision, those collisions are elastic. The total energy, EK, K means kinetic energy, total kinetic energy of the gas particles is constant, and that can be calculated using 1/2 of mv squared. V is the velocity, m is the mass. We said right here, gas are considered to have mass, so they do have mass, okay? Since the density of gas is pretty low, so therefore there's plenty of empty space between the gas particles or molecules, and because of that, the attraction between particles or gas molecules is negligible. The average kinetic energy is directly proportional to Kelvin temperature. The higher the temperature, the faster the particles move, and then the greater the kinetic energy. And then the greater the kinetic energy. Now let's concentrate on the velocity of gas particles. It should be pointed out all gas particles in a sample, they can travel at different speeds. Therefore, the distribution of speed follows the Boltzmann distribution pattern. So a bell-shaped pattern. And this is the fraction of particles, gas particles, and this is the speed or velocity of gas particles when they move, okay? Very high fraction of gas particles, this is the highest point, travel at the average speed or mean speed, all right? So here's the low speed, here's the high speed. This tells us very few gas particles travel at a very low speed, and the same thing is true for the high speed. Very few particles travels at a very fast speed. Okay, so that's the Boltzmann distribution. There are different ways to calculate or estimate the average velocity. The most common way actually is called root mean square RMS method. So this is the root mean square velocity that actually can be calculated using the square root of the sum of the speed or velocity squared over n. And then we can say this is the root mean square average velocity. So U again is the velocity. In order to have the same average kinetic energy, you see, the average kinetic energy, if that's the same, then the heavier molecules must have smaller average speed. So this is basically the equation we learned a while ago. Kinetic energy equals 1/2 mv squared. Na here is the Avogadro number. We can also write the kinetic energy, average kinetic energy equals 1.5 RT. R again is a constant, but please note in here, the constant for R is not the one we used previously. So this is 8.3 joules over mole and K. 1 joule is defined as 1 kilograms times meter squared over second squared. So if we equate and solve those two equations, we'll get actually Avogadro number times mass equals molar mass in kilogram per mole. You see, molar mass. If that's the case, then 1/2 times molar mass times the root mean square velocity squared equals 1.5 RT. So basically, this part equals this part. That's basically what it says right here. And then we can have this equation. We move 1/2 of mm over the other side. So then finally, we have a new equation, the square root of 3 times RT over molar mass. That gives the velocity. And now from this velocity, you see, if the molar mass is greater, or let's say if you have a heavier gas, then this value will be smaller. Therefore, the velocity is lower. If you have lighter gas, then this molar mass, of course, is much smaller. Then this term should be much larger. And of course, then the velocity or the speed of the gas particles or molecules will be much faster. And that explains why heavier molecules have slower average speed. So that's the reason. Now let's look at the relationship between velocity and temperature. We already said a while ago, the velocity is directly proportional to the absolute temperature. So as you can see, this is the velocity of the gas, and here is the relative number of hydrogen molecules with the indicated velocity. Right here is the velocity. So it means right here, there's a maximum of nitrogen molecules traveling at this speed right here, at this speed. You see, at lower temperature, 273 K, that's the 0 degrees Celsius, the average speed should be somewhere here. So the average speed somewhere here, is all right? Compare with higher temperature, 1000 K, the average speed is here. So at 1000 K, the speed is faster than at 273 K. And at 2000 K, you see right here, the average speed is even greater, is even higher. All right, because the speed is this way, is the x-axis. So therefore, as absolute temperature increases, the average velocity increases. Okay, and also the distribution function spreads out. You see, at a higher temperature, it spreads out. Unlike at the lower temperature, it's a very narrow band. All right, and that results in more molecules with faster speeds. You see, of course, here there are more molecules. This is the faster speed. So therefore, there are more molecules with a faster speed. But at a low temperature, you see very, very few particles has faster speed. Let's work on example 56-1. Calculate the root mean square velocity of nitrogen at 293 K. Let's write down what do we know and what do we need to find out. We need to find out the URMS. We need to find out the velocity, the RMS velocity. We know molar mass, we know absolute temperature, so we just need to use this equation to find out URMS. Okay, write down this equation again. 3 times R constant again. This is a different R constant and with a different units times absolute temperature divided by the molar mass. Okay, divided by the molar mass of nitrogen N2. Since in the units for R constant we have kilograms, not just grams, so therefore we have to convert this molar mass from grams to kilograms. And now 511 meters per second, that's the speed for nitrogen molecules traveling at 20 degrees Celsius. 293 K, that's 20 degrees Celsius. You can see that's very fast. 511 meters per second, that's very fast. Diffusion versus effusion. So what is diffusion? In this case right here, we have this divider. Once we remove the divider, so the concentration of gas on this side is high, on this side is virtually zero, very low. So therefore, the gas particles, they should move from high concentration to low concentration. So the concentration in any part of this container is the same, unlike before we remove the divider. Here is very high on this side, here is zero. All right, so that's diffusion. And then effusion, very similar, but this time we don't remove this divider. Instead, we just open a small hole right there. The gas particles or molecules can only pass through that tiny hole. You see, pass through that tiny hole and migrate into the low concentration zone until the concentration on this chamber, the red chamber, equals the concentration of the gas in the left chamber. Then those movement will stop. This is also a kind of diffusion, but we call this particular diffusion, we call that effusion. Okay, so And here, after that divider is moved, all the gas particles, they are free to travel to the right part of the container. All right? So there's no restriction. But that's diffusion. But effusion, no. You can only, the gas particles can only pass through that tiny hole, traveling from high concentration zone to low concentration zone. So that's a difference between diffusion and effusion. Both the rates of diffusion and effusion of a gas are related to its root mean square average velocity. The rates of diffusion and effusion of a gas are related to its RMS, root mean square average velocity. And at the same temperature, this simply means that the rate of gas movement is inversely proportional to the square root of the molar mass. This brings up the Graham's law of effusion. For two different gases at the same temperature, the ratio of their rate of effusion is given by this equation. You see, the ratio of the rate of gas A over gas B can be calculated using the square root of molar gas of B over molar gas of A. Now let's work on one calculation involving effusion of gas. Calculate the molar mass of an unknown gas that effuses at a rate of 0.935 times of nitrogens. Look at what's given. So the rate of the unknown gas over the rate of nitrogen gas, that's given. What do we need to find out? We need to find out the molar mass of unknown. Okay, of course we have to use this equation right here. Okay, so we have to use that. And where did we get that equation? We get that equation, of course, from Graham's law of effusion. And from this key equation, we should be able to find out the molar mass of unknown gas. We move this to the left-hand side, and then keep the molar mass of nitrogen on the right-hand side. Then we'll move this term to the right-hand side as a denominator. That's how we obtained this equation. So this equation we are going to use to solve this problem. Okay, so molar mass of nitrogen, then the ratio of the two squared, that's 32 grams per mole. Again, what is this unknown gas? Has to be oxygen gas. That's it for lecture 56. I will see you in lecture 57.